first, thank you, Ong, for your kind acceptance to give this this presentation online. It's quite late now in Sydney. It's already 8 p.m. So thank you very much for this. And on behalf of IRT SystemX, so I welcome you and I welcome all the colleagues and all the online attendees to this presentation. So first, I will give a short introduction of Dr. Ong's bio or background. So Dr. Ong Liu is Associate Professor of Engineering Design at the School of Mechanical and Manufacturing Engineering at the University of New South Wales in Sydney, Australia. He obtained his PhD in Mechanical Engineering at the University of Southern California in US in 2012. He was a visiting assistant professor and manager of the Viterbi iPodia program, which is a famous online learning program developed at the University of Southern California. And he joined the UNSW as a senior lecturer in 2016 and was promoted to associate professor in 2020. Dr. Liu's research interests include design thinking, design methodology, intelligent manufacturing, digital twin, artificial intelligence, and engineering education. Dr. Liu is a fellow of the American Society of Mechanical Engineers, associate member of the International Academy for Production Engineering, CIRP, invitational fellow of the Japan Society for the Promotion of Science, fellow of the Institution of Engineers Australia, and senior fellow of the Higher Education Academy. Dr. Liu is also the vice chair of the SIRP Scientific Technical Committee on Design, and he received multiple prestigious awards, such as Parks Best Journal Paper Award, UNSW Vice Chancellor Award for Outstanding Contribution to Student Learning. He is also one of the 250 top researchers by the Australian Research Magazine, and Best Paper Award by an important journal, which is the Journal of Manufacturing Systems, etc. So Dr. Liu is associate editor of the Journal of Intelligent Manufacturing, and he serves in editorial boards of multiple renowned and prestigious journals. So, Dr. Liu, thank you again for accepting this presentation, and so now the floor is yours.
Thank you, Nabil, for the introduction, and also thank you for the invitation. It is a great pleasure and also a privilege to make this presentation. So, as the title of my presentation suggests, in this presentation, we want to look into the overlapping area between digital twin and artificial intelligence and also data in the context of engineering design, and to see hopefully how we can synergize between digital twin, AI, and data, and to collectively drive this paradigm shift of engineering design towards data-driven design. So this is the presentation outline, and basically I'm going to cover 3 topics, and data-driven design, digital twin-driven design, and AI-driven design. So a lot of topics to be covered, and so in the context of engineering design. So in other words, the end of this paradigm is to make design more data-driven instead of experience-driven. So the means we want to apply to achieve this end is digital twin plus artificial intelligence. So first of all, I want to reflect a little bit background about this digital twin and artificial intelligence, how they emerged and why they're important. And I think the general context is Industry 4.0, which is a notion many of you are familiar with. And the only thing I want to point out is that Industry 4.0 as a paradigm has impacts not only on the production side, meaning the manufacturing side, but also it has a lot of impacts on the distribution side and also on the consumption side. And it can be argued that Industry 4.0 also changed customers' behaviors And today's customers, for example, they demand higher requirement and for personalization and customization. So this actually requires a lot of these data-driven approaches. Because traditionally, we can easily customize products and based on the traditional customer methods. But nowadays, because customer requirements for personalization of products become very high, and it requires additional data-driven approaches. So if we look at this digitalization in Industry 4.0, and so we can see that on top of this triangle of production, consumption, and distribution, and we have this additional dimension called digitalization. So basically, for everything in the physical world, and if we can create these digital replicates, and then you have this digital world. And of course, they have different names, such as metaverse, such and such. And so I think the hope is that through this digitalization, and we can project the values generated in the physical world into this digital world. I think this is the background of this Industry 4.0. So now we also talk about Industry 5.0. And people still arguing about what does Industry 5.0 mean. And as it happens, for example, in Japan, they actually also raised this notion called Society 5.0, which is in correspondence to Industry 5.0. So like I said, even though there are a lot of debates about what does Industry 5.0 mean, and I think one thing most people agree is that Industry 5.0 is human-centric, meaning that we need to keep humans in the loop of decision-making, of course, including design decision-making. And in this process, we need to actually require a lot of these data-driven insights and human wisdom, and how these two can be synchronized. So digital twin emerges from Industry 4.0 to 5.0. So here I actually use this 5-dimensional model proposed by Fei Tao, and I think he already gave a presentation for this event. And so if we look at this 5-dimensional model of digital twin, a typical digital twin includes 5 components. You have a physical product, you create a virtual entity, and then you have this connection between the physical and the virtual entity, and then you have the data generated by both physical and virtual entities, and then you also provide additional service and to, for example, improve the performance of the physical entity and to increase the fidelity of the virtual entity, such and such. So the applications of digital twins can be found in different fields, and especially in smart manufacturing. And smart manufacturing by itself is also a data-driven paradigm. So it can be argued that engineering design lies in the upstream of smart manufacturing. In other words, data-driven design also lies in the upstream of data-driven manufacturing. And it can be argued that engineering design generates a lot of values because it lies in between manufacturing and marketing. Okay, so in the upstream of data-driven design, we also have data-driven marketing. So this is how the whole value cycle is established. So here are some value propositions of digital twin to design. And actually, most of these value propositions were raised about 5 years ago. And when we actually wrote the first paper about using digital twin to support design decision making, and we can see that a lot of these propositions now, back then they are very conceptual, but now I believe that a lot of these propositions are already being realized. So the first proposition is that digital twins can enable designers to identify inconsistency. So here we actually use this FBS model, which is a famous design ontology. So basically, we use this model to indicate that digital twin can be used to help designers realize the inconsistency between the expected world, interpreted world, and the physical world. So this is, of course, in terms of function, behavior, and the structure. So we can use digital twin to monitor the inconsistency between the three worlds and then try to make improvement accordingly. So another value proposition is that digital twins can enable designers to manage uncertainty. And because uncertainty is a very important thing that affects a lot of the quality of design, for example, robustness, reliability, complexity, and such. And we can use digital twins to help manage uncertainty. And the digital twin can also enable designers to manage their knowledge and also to enable designers to enhance collaboration. So traditionally, a lot of the collaboration happens in the physical space, but with digital twin, now it is possible to also project this collaboration into the virtual space, the digital world. And finally, digital twins can enable designers to enhance adaptability of products and to make the products not only more functional, but also more adaptable and to new context, new environment, new dynamic changes. So when we talk about digital twin in design, so we have to understand what are we talking about? What's the paradigm? Okay, so if we look at engineering design is an open-ended field. And as design researchers, and we are used to incorporating knowledge and methodologies from other fields and to enhance design decision making. For example, when we combine engineering design with biology, we have this biologically inspired design. So basically, we get inspirations from biological systems and to design more functional engineered systems. And when you combine engineering design with decision science, you have design decision making. And when you combine engineering design with cognitive science, you have a lot of studies about design cognition. So when we talk about interdisciplinary integration between design and digital twins, so a lot of researchers, including myself, and we try to promote this notion called digital twin-driven design. In other words, how do we use digital twin to drive the design decision-making process? So what is data-driven design? Because after we understand a little bit of context about digital twin, because after all, digital twin is only the means. The end we are trying to achieve here is still design, how to make better design decision-making. So we need to understand what is data-driven design. So data-driven design relies a lot on the data science. So a lot of these propositions are actually retrieved from a previous keynote me and Nabil we published for CIP last year. So this is about how to promote engineering design from experience-driven design towards data-driven design. So data-driven design means the practice of basing design decisions on insights and predictions derived from data, rather than purely based on designer experience. So like I previously suggested, data-driven design is a subset of data-driven X, including data-driven manufacturing, data-driven marketing, data-driven innovations, and such. So this is a whole value cycle. So the value propositions of data-driven design include automatic decision-making, and predictive analytics and insight extractions. So if we compare this data-driven design versus digital twin-driven design, so how are these two notions similar and different from each other? So if we look at the definition, digital twin-driven design relies on real-time virtual replicate of a physical product. And data-driven design, on the other hand, the data source and is more broad and it's broader. It comes from a broader channels of data. And the data can be real-time data. It can also be historical data. And if we look at the role of simulation, and we know that simulations play a very important role in digital twins, but in data-driven design, simulation is less central. They are still important, but they actually use a lot of this real-world data in data-driven design as well. So when it comes to the integration with IoT, and the digital twin actually have a very strong integration with IoT and to acquire this real-time data. And in terms of the integration of IoT in data-driven design, so IoT data is a very important source of data-driven design, especially for the design of smart products. But this is certainly not the only kind of data used in data-driven design. And in terms of flexibility, and the digital twins is more flexible for complex systems requiring real-time feedback. In contrast, the data-driven design is more suited for iterative improvements based on historical data. So in terms of the application scope, and the digital twins, they are best for some complex ongoing products, and especially these high-value products and processes. And in contrast, data-driven design can be used also for consumer products, software, and trend-based markets. So if we look at the complements between data-driven design and the digital twin-driven design, so our proposition is that digital twin can help overcome multiple data-related challenges in data-driven design. Because in the paper we published for CIP and about data-driven design, we identified a number of data-related challenges in data-driven design. And we believe that digital twins can actually help address some of these challenges. So one data-related challenge in data-driven design digital twin can help address is data sparsity. Data sparsity basically means that in reality, we want to use data to drive design decision-making. And the dilemma is that we don't have a lot of high-quality data. And high-quality data also is very expensive to acquire. And on the other hand, if you use this low-quality data to drive decision-making, and the quality of decision-making becomes lower. So this is a dilemma. So in this case, we can use digital twins to help create this something called synthetic data, meaning that these are the real high-quality data, but they are generated using simulation and the integration between simulation and the real-time data. And in this case, we can use the synthetic data as a means to address this problem of data sparsity in the context of data-driven design. So this is basic means, the synthetic data, this is a rapidly evolving area. As a matter of fact, I think just last month, and Meta actually acquired a major data labeling company in the US, and for a very big, very expensive price. And so data, and especially synthetic data, the values is being increasingly realized. So digital twins can also be used to address the data quality issue in data-driven design. Because data quality, this is a multi-dimensional notion, including data relevance, data timeliness, data completeness, data consistency, and data accuracy. So we can possibly use digital twins to help improve the data quality. Okay, because in reality, if we want to use real-world data to drive data-driven design decision-making, sometimes the manufacturers face this dilemma. So on the one hand, the cost of using poor quality data is very high. Because if you use poor quality data to train your model, and the outcome is likely to be affected. But on the other hand, if you want to improve the data quality, meaning the real world data, and it involves a lot of additional cost to improve the data quality measures, implement data quality measures. So this is a dilemma. And in this case, digital twin could be a promising solution because the cost of generating high quality or acquiring high quality data using, for example, simulation or IoT becomes relatively lower. So another possibility of using digital twin for data-driven design is to improve data privacy. For example, in Europe, they have this regulation and GDPR about how to protect privacy. And technically, a lot of the data involving privacy, sensitive data, cannot be directly used for design decision making. In that case, maybe we can use digital twins to get some mask to this data and to also combine this real world data with synthetic data and to overcome these data privacy limitations. So, and also we can possibly use digital twins to improve the bias. Because when we use the algorithms to drive decision making, so a lot of bias will emerge. And from data to algorithms, from algorithms to users, from users to data. So we can possibly use the digital twins to create synthetic data and to try to cover this bias and correct this bias in these data sets. And also another challenge in data-driven design is fairness. And for example, for some customers, we have a lot of data. For some products, we have a lot of data available. But for other products and other customers, we have limited data. So in that case, we can also possibly use digital twins to resolve this fairness issue in data-driven design. So far, I talked about data-driven design. I also talked about digital twins and how we can use digital twins to resolve some issues in data-driven design. So another important technology emerging in recent years is artificial intelligence. So I want to use some research conducted by my own group and to indicate how does AI fit into this overlapping between digital twin-driven design and data-driven design. So first of all, if we look at AI's abilities, and in the x-axis, and we have different kinds of problems: known problem, unknown problem, and emerging problems. And in the y-axis, we have different kinds of abilities required in design decision making. For example, design basically requires three categories of abilities, and namely descriptive ability, prescriptive ability, and predictive ability. So even before we introduce artificial intelligence in design, designers, they can use some traditional methods, traditional tools to support this description and prescription related problems. But designers are not known for their abilities to make informed predictions in the past. So this is a very important skill AI can provide. So like I suggested, the predictive ability of AI is especially important to engineering design. But on the other hand, the challenge is that especially a lot of the AI we use now, large language models and generative AI, ChatGPT, Gemini, and they are so-called the general purpose large language models. So they may not be trained based on specific domain knowledge. In other words, a key challenge is how do we convert the general purpose large language model into domain specific ones. So in this process, data and digital twins, they could play very important roles. So here I just want to introduce a few research conducted by my own group and in correspondence to their time, just to show you what we have been doing. And then we're going to maybe discuss a little bit how we can possibly use AI better in the context of digital twin-driven design, data-driven design. So this was a research we conducted about 5 years ago. That was actually before the emergence of ChatGPT. So basically, we use this AI and to actually analyze customer reviews and user-generated content about the products, and based on which we try to classify product features into different categories based on this Kano model. Kano model was a very traditional design method, and traditionally designers have to use a lot of this surveys, interview data to drive this process. But with artificial intelligence, we can actually use AI to automatically interpret customer voices based on which to classify product features into different categories. And back 5 years ago, and that was still quite new, but nowadays we can easily use ChatGPT large language models to do that. So another research we conducted is to introduce knowledge graph into product design. So the basic idea is that for the design knowledge, and we want to represent knowledge into this graph structure, basically in terms of entities connected by different links. And then we use machine learning and to train the machine learning, to train AI to learn about this knowledge graph, based on which to predict new knowledge, to predict knowledge that is not known yet. So this is another study that introduced knowledge graph into product design. So in this case, the case study we conducted is to use the knowledge graph for a functional design. So this is another research. In this research, we introduced this notion called federated learning, and to improve to address the privacy issue and in the design of smart products. Because when we design the smart products, and traditionally we have to transfer product data directly with the central model, and then the model is trained centralized. But this will violate this privacy limitation. So in this case, we're actually using this federated learning. In other words, the model training is performed locally instead of centralized way. And then we only transfer the model updates to the central server. And then these model updates will be aggregated in a centralized way. So in this way, this will actually overcome the limitation of privacy protection. So this is another study. So basically, we introduced this notion of explainable AI, XAI, and into product design. So the basic idea is that most of today's AI, they are so-called this black box, meaning that we only know the input and output. It's very difficult to know what's happened and why these output predictions are made based on the data. So XAI, explainable AI, basically means that on top of this black box AI, we also create this transparent AI. And then we use this transparent AI to explain the behaviors of this black box AI. And in this study, we actually try to evaluate how does this explainable AI helps designers make more informed decisions, and also whether this improves designers' trust in AI predictions. So in recent years, and the focus is of course on large language model. So we conducted also some studies about using large language models in different aspects of design. And in particular, if you compare today's large language models are traditional expert systems, because that's when AI was first introduced in engineering design. We developed a lot of these expert systems. But if you compare large language models with expert systems, a very significant difference is that today's large language models are so-called generative AI, meaning that they can generate stuff that does not exist yet. Because if we look at ChatGPT's OpenAI's classification of AI, in the very bottom we have this conversational AI, and in the next level we have the reasoning AI, and in the next level we have the design agents, AI agents. In the next level we have the innovating AI, and finally they have this organizational AI. So compared to the traditional expert system and today's large language model, they are generative AI, meaning that they can create new knowledge, new concepts that doesn't exist yet. So that's what we consider a very natural fit to engineering design. And another reason is that, especially in the early stage design, designers use a lot of language to communicate their ideas, to communicate their design ideas. So this is actually also another reason why large language models is a particular fit. So large language models are increasingly popular. A lot of different large language models are being developed. And when it comes to large language models, especially in the context of engineering design, there are different perspectives about how to interpret large language models. One way to interpret large language model is to treat them as something called the search engine. That was the very traditional view. And that is actually, basically, you retrieve large language model as a way to retrieve knowledge. The assumption is that the design knowledge is already there. The design knowledge is there. And you just use the large language model to try to find it and retrieve it, adapt the knowledge to a new problem. That's the very traditional viewpoint. And of course, this kind of approach has a lot of these challenges. In particular, this is something known as the generative errors. And because today's large language models are generative AI, and in the process, if you generate a lot of entities that doesn't exist yet, and so this will include a lot of these generative errors. And this is where we consider digital twin to be quite applicable, because digital twin is a digital replicate of physical products in the digital world. So if we use these digital twins as a means to maybe correct these generative errors, so this is a very good complement. So another perspective to treat large language model is to treat large language models as workflow facilitator. Basically, we know design, this is a process we need to follow. There is a workflow. The workflow have different operations. And so we basically use large language models as a facilitator of these workflows. And here, of course, you have a lot of advantages, including natural language understanding, task decomposition, knowledge integration. But in the meantime, they also have a lot of these challenges. And in particular, this data dependence, meaning that the performance of these large language models and depends a lot on the data used to train the large language models. And meaning that effectiveness is also affected by the data available. And in this case, this is also where digital twins can come into play. And because digital twins is digital replicate of physical products, and if we use digital twin data to fine-tune large language models, so this could improve the effectiveness of workflow facilitating. So finally, large language models can also be treated as reasoning facilitator. And this is a relatively recent perspective about large language model. And because even last year, people still are arguing about whether today's large language models are equipped with reasoning abilities. But starting from this year, I think many people started to believe that large language models can at least handle some reasoning tasks. Not every reasoning task, not those very complex reasoning tasks, but for some reasoning tasks, and large language models are certainly capable. So applications of large language models as human collaborators. So this is a perspective I want to emphasize, because based on this perspective, and we think this will introduce a lot of opportunities to data-driven design and digital twin-driven design. So the basic idea is that instead of treating a large language model AI as a traditional tool, and we try to treat AI as a potential collaborator, as a counterpart. and play different roles with different personalities in the design process. So this is the perspective we adopt in our research about large language model. So we have conducted a lot of research about using the collaboration between AI and human in the context of design, data-driven design. So we use different approaches. So the approach we used in the past was prompt engineering. So the basic idea is that if designers use different kinds of prompts and the different synthesis of prompts to interact with large language model, the output from large language models could be very different. In other words, if you use more structured prompts, smarter prompts to interact with large language model, and hopefully the result will become better. So based on this hypothesis, and we developed this classification of design-specific prompts. And so basically, we classified design-related prompts into different categories. We use this IDEF0 modeling methods to classify these prompts into input, output mechanism, and control-related prompts. And then we also studied the impacts of these different syntheses of these prompts and to see what's the best synthesis strategy and how do they affect the effectiveness of interacting with large language models. So recently, we also look into this large language model customization and personalization. So these are two different notions in the context of large language model. Basically, customization means that we want to customize a general purpose large language model into a very specific domain or field. And personalization means that we want to personalize the large language model according to, for example, the preference, background, and experience of individual users. And in this case, the approach we use for the customization is something called RAG, Retrieval Augmented Generation. And so basically, you use domain-specific data to customize large language model, general purpose large language model to make them more domain-specific. And the personalization is still achieved by prompt engineering. Okay, so here are some advantages and the limitations of using large language model in the context of data-driven design. So here I want to elaborate a little bit about these future challenges of data-driven design. Because so far we talk about digital twin-driven design, AI, and a lot of different concepts. So we want to know what are the future opportunities, what are the future challenges for design researchers. So we believe that the first challenge is how to keep designers in the loop. Because nowadays we use a lot of this AI, and now we are developing the autonomous AI agents, and hopefully AI can perform some design operations autonomously. So in this case, especially in the context of Industry 5.0, Society 4.0, and we need to ask ourselves how to keep designers in the loop of design decision-making in terms of human values, ethics, model selection, model fine-tuning, outcome evaluation, data quality assurance, and method integration. So another challenge is that how do we facilitate the collaboration between designers and digital twins and AI? Because nowadays, a lot of these design operations and AI are becoming digitalized. And how do we facilitate the collaboration? Because traditionally in design, we also do a lot of collaboration between designers and, for example, in global product development teams. But in this process, we develop a lot of these collaboration frameworks, methodologies, process. But most of these frameworks, they are developed for the context of human-to-human collaboration. But in this new context of human-AI collaboration, human digital twin collaboration, the traditional collaboration frameworks are no longer applicable. So we need to ask ourselves, do we need new collaboration frameworks to facilitate this digital twin AI designer collaboration, or we need to adapt the traditional frameworks? And if so, how do we do that? And finally, and the next challenge is that we also need to address this generative AI, because generative AI is applied not only in the conceptual design, but nowadays we also use a lot of this generative AI in the physical field. For example, design for additive manufacturing. And so in that case, that involves a lot of concerns about reliability, about safety. And so this is actually where you also have a lot of challenges. So the next category of challenge is accountability and contestability. So basically, if we use a lot of these digital twins and AIs to make decisions, and instead of human designers, and we need to understand how do we hold algorithms accountable for the design decisions they made. And meanwhile, we need to also enable human designers to contest machine predictions, machine AI or digital twin decisions in the process. So here, this is also two challenges. That's also more related to human in the loop. So finally, we also need to ask ourselves, what is the most effective way to evaluate digital twin-driven design, data-driven design, and AI-driven design? Because if you look at a lot of this existing literature, a lot of the existing studies, and they use a lot of these metrics, for example, from AI, from computer science, to evaluate data-driven design, digital twin-driven design. But this is not the most effective way to design the evaluation methodology, because in this case, they actually ignored a lot of these metrics from the domain, from the design. And so how to design better evaluation methodology for this emerging research, and in terms of metrics, procedure, organization, and impacts. So this is also introduced a lot of challenges. So finally, I want to indicate some future research opportunities. And now if we look at this framework, in the x-axis, you have in one extreme, you have the physical space. In another extreme, you have the digital space. And the y-axis indicates the centralized paradigm and decentralized paradigm. And the z-axis represents product and service. So we can see that we conducted a lot of studies about this. So the opportunities lies in decentralized services in the physical space, and also the decentralized products in the digital space. So this is where we believe have a lot of opportunities. So in summary, so we try to cover a lot of topics today. And so basically, I want to draw the reader's interest and audience interest about these three different notions: data-driven design, which is a means, and digital twin-driven design, which is ends, which is a means, and also the AI-driven design. In other words, we want to look at the overlapping between data, digital twin, AI in the context of data-driven design. So we talk about a lot of value propositions of digital twins for data-driven design, and we also compare the difference between data-driven design versus digital twin-driven design, and to see how digital twin can help address some data-related challenges in data-driven design. And so I believe that digital twin is still at the innovation stage. So there are a lot of future opportunities, and especially the complements between digital twin, AI, and especially how they can actually use data created by digital twins to support, to fine-tune general purpose AI to make them more domain specific. I believe that in that area, this is still a blue ocean, and which includes a lot of opportunities. So thank you for your attention. This concludes my presentation. Thank you.
Okay, thank you. Thank you, Ong, for this very interesting and comprehensive presentation and the focus on the overlap on data, digital twins, and AI for the purpose to improve design and engineering design. So I think we have time for questions, and I think we will have some interesting questions maybe from the audience. So I don't know if someone would like to start with the question. I have to check on the audience. Yeah. So Abdelhadi, maybe you can open your mic and ask directly the question to Ong.
Yeah, thank you very much, Professor, for your presentation. It was really interesting and insightful. First of all, can you hear me well before starting my question?
I think so, yes.
Okay, we try to raise my voice. So I would like to go back to the impact of the poor data that you have mentioned on the decision process and the expensive cost acquiring the qualitative data actually to improve this decision making. So I was wondering, have you investigated how the fidelity of digital twin influences actually the process of decision making using the digital twin? So which is in contrast with robustness and reliability.
Thank you for the question. I think this is a very important question. And because, like I said, I think one of the value propositions we raised about using digital twin to drive decision making is to improve, to reduce uncertainty, and which is a very important factor for improving, for example, reliability, robustness. And so, yes, I think to answer the question, I think theoretically, conceptually, yes, but in reality, no, we haven't looked into that. But I do believe that there are a lot of opportunities in this field, and especially in terms of how to improve the data quality and using maybe synthetic data, and also how to use digital twin data to create a better representation of the product state. And from that perspective, yes. And another thing also related to your question to reliability is complexity. Because a lot of the products we are using digital twin, they are the complex products or complex process. And so from design point of view, and this involves not only, how do I say, uncertainty, but also involves a lot of the coupling. So how different components are coupled with each other. So I think this will also have a lot of opportunities in that area.
Yeah, thank you. Thank you very much for the response.
Thank you.
Okay. Thank you, Abdelhadi. Other questions? I just check on the screen. Sorry? Okay. Maybe Stefan?
Yeah, thank you for the presentation. I just have a question that I put in conversation. I was wondering if there was any studies when it's a good decision to build a digital twin. So if there's some studies about return on investment on building digital twin for doing DT design against doing traditional data-driven design.
I think this is a very good question. And because so far, especially a lot of the research conducted about digital twins in the context of manufacturing, I think this is mostly from this technological perspective and how to do that and what's the right. And I think a very important perspective is actually to evaluate this from the economic perspective. So that's, for example, related to the cost of developing digital twins and what has going to be the values. And for example, if, for example, using, this is the reason why we mentioned that a digital twin, a possible challenge it can address in data-driven design is data quality. Because nowadays, if we want to acquire high quality data, and for data-driven design, it's very expensive. So in that case, using digital twins, if digital twins can solve synthetic data, and I think that actually reduce the cost. But I think we need to actually develop a more holistic framework to evaluate the whole life cycle of digital twin, because after all, digital twin is just a means. And how do we use these digital twins to support design decision making? And first of all, I don't think it's my personal perspective, I don't have empirical evidence, of course, is that I don't think it's very economically sustainable if we just use digital twin to support design decision making. But if we have a more holistic framework to evaluate the cost implications of digital twin to the whole value creation chain, I think that will be very interesting research. And another thing I want to mention is actually AI, because in this case, and at least my own students, now they are looking into the option of using AI to automatically develop digital twins. Because nowadays, if you look at the OpenAI's classification of AI, and in the middle, they have something called design agents. And so if we can use AI to develop not a functional digital twin, but some components of digital twin, this will also reduce the cost of DT development. So to answer the question, I do believe that we need some frameworks to evaluate the cost implications of digital twins, but not only to design locally, but to the whole value creation chain globally.
Okay, thank you.
Okay, so we have a question from Fauzi. Maybe can you open your mic and ask directly the question?
Yes, thank you, Professor, for this great talk. So my question is in continuity about Abdullah's question about the domain gap evaluation in terms of robustness of digital twin.
Yes.
So I think that we know that when we use synthetic data, most of the time we have a gap between performances in real time or in real world and in virtual world. So do you plan to evaluate or integrate this evaluation of domain gap in your framework?
Yeah, this is also a very good question. So because in the context of engineering design, we have actually a lot of approach for how to evaluate and improve robustness. And especially, for example, in Japan and in their manufacturing industry, they have a lot of such studies related to robustness. But the difference for digital twin is that a lot of these traditional methods or evaluation frameworks they developed are for the physical product. And but digital twins, as we all know, not only it's a digital replicate, but also the integration between physical product and digital replicates. So to what extent we can directly use these existing methodologies, this is questionable. And another thing I want to mention is that because a lot of these studies about robustness, they deal with, for example, uncertainty and functional coupling. But in the context of digital twin, because relies a lot on the software, and they also have to deal with a lot of these non-functional requirements. So to answer the question, I do believe that there are a lot of interesting studies to be conducted along the questions you suggested. That is, how do we adapt the existing design, for example, methodologies, frameworks about robustness of physical products? How do we test them for the digital twins? This will be, I think, some interesting research to be conducted. Of course, I don't have an answer to that yet.
Thank you, Professor.
Yeah, but in short, I don't believe it's fair to use the traditional definition and evaluation framework of robustness to evaluate digital twins, because the contexts are quite different.
Any other questions from the audience?
Yeah, perhaps one question. Still a few minutes. First of all, thank you very much for your very clear presentation. So I have one question. Actually, it's about your opinion. In the context of the industry 5.0, in which the human centricity is one of the most important criteria, what do you think about the acceptance of the data-driven design comparing to the digital twin design, such as the second one? We still have this accordance with the physical aspect, comparing to the data-driven, which sometimes we will lose this physical aspect. So what do you think about the acceptance of collaborator for full data-driven design, compared to the digital twin design?
You mean the acceptance level?
Yeah, that the collaborator will use the full data-driven design compared to digital twin design.
So first of all, I think these two paradigms, they are not. I think they have some overlapping. So I think these two paradigms, this data-driven design or digital twin-driven design, I think they have overlapping, and especially in terms of data. Because data-driven design, we can use a lot of data that's not necessarily generated by digital twins. But on the other hand, in that digital twin-driven design, and for example, we mostly use digital twin-driven design, for example, for these complex products or complex process. And for example, in data-driven design, we can actually use this paradigm to do a lot of these consumer products. So I think the contexts are not entirely the thing. But if we look at the overlapping between the two, and I do believe that you will find most opportunities in the overlapping between the two. For example, suppose we can find a scenario where we can use the synthetic data and generated by digital twins and to drive the decision making. And in that case, for example, maybe it's very difficult to acquire the real world data. In that case, this will generate a lot of values. And I think that's my perspective. In that case, I think the acceptance level will be the highest, so to speak. So my point is that digital twin-driven design and data-driven design, sometimes 1 + 1 is larger than 2, sometimes it's smaller than 2. It depends on the context. For example, if you just want to design a vacuum cleaning robot at home, in that case, maybe we don't need to have digital twin-driven design plus data-driven design. We can have maybe data-driven design is better. But for some scenarios, for example, for the design of very complex products, and when it becomes very expensive to get this physical data or not reliable physical data, in that case, maybe digital twin-driven design and data-driven design can generate better values. That's my perspective.
Okay, thank you. So I have also a question, because you write something very interesting in terms of collaboration. So the digital twin as collaborator. And this is maybe something that could be important in the future. Can you elaborate more, finally, on the role of digital twins as a kind of design collaborators?
This is a very good question. Thank you, Nabil. So to me, I feel like digital twins could be an embodiment of AI in collaboration. And because if you look at digital twin human collaboration, and so I think there are two kinds of collaboration we need to look at. The first one is, for example, collaboration between digital twin and the designer. And the other collaboration, for example, is between AI and the designer. And AI is intangible, and the digital twin is not. I mean, digital twin has an embodiment. So to me, I feel like maybe the better opportunity is to use AI, in other words, as the brain of digital twin. And because digital twin has an embodiment, the embodiment is built based on the physical reality, means that this can be accepted by humans easier. But meanwhile, if we can use AI to increase the intelligence level of this embodiment, and I think together, this DT plus AI, and will be a better collaborator than either DT or AI separately. I'm not sure if that answers your question, but
yeah, thank you. It's very, very interesting, and I think we will have a lot of discussions about the role of AI and digital twins in engineering design in near future within our community.
I think the whole idea I want to present here is that if we are able to, I'm not saying that digital twin AI data should all be integrated into this data-driven design. And this involves very high cost. Maybe the values will not be enough to justify the high cost. But I do believe that in certain areas, and if we find a very good scenario and or case, and I do believe that data-driven design can be complementary to digital twin-driven design, and AI can also be integrated with digital twins to facilitate human-machine collaboration. That's my perspective.
Okay, so if no other questions from the audience, so maybe we can stop here. So Ong, thank you again. Thank you very much for your kind presentation.